these calculus videos, written and performed by me, Patty Leitner.
Part 4. Integrals. Section 5.3. The fundamental theorem of calculus and the definite integral.
Lesson 2. A proof of the fundamental theorem of calculus. We've been using this fundamental theorem of calculus, but we have not yet proved it. And there is a rigorous mathematical proof in your textbook. It is not too hard to follow, but it doesn't give you a real feeling for why the fundamental theorem of calculus would be true. It seems like a very mysterious connection between these antiderivatives and the area under a curve. So actually we are going to do a kind of picture proof. It's not a rigorous proof, it's more of a persuasive argument for the fundamental theorem of calculus. But although it isn't rigorous, I think it will give you more of a feeling for why the fundamental theorem of calculus is true. So that's what we're going to be looking at next. But before we dive into that proof, I'm putting that in quote marks, I want us to review something from back in chapter 2 because we will need it for this picture proof. And it's something that sometimes we forget. I want you to think way back in this semester to when we were doing limits of this form. The limit, as h approaches 0, of f of x plus h minus f of x over h. We've had occasion to use this particular type of limit only a few times since we first introduced it. Do you remember what that limit ends up being equal to? It was our original definition of f prime of x, our original definition of the derivative of our original function f. So limit as h goes to 0 of f of x plus h minus f of x over h. Remember that expression, this fractional expression here, is really the slopes of the secant lines, and as h got closer and closer to 0, our secant lines got closer and closer to the slope of the tangent line, and the slope of the tangent line is f prime of x. So I just wanted to remind you that when you see this limit, you can replace it with the derivative of f prime of x. What about these two limits? What if I had the limit as h goes to 0 of capital G of x plus h minus capital G of x all divided by h? Well, it's the same exact limit, except it's a different function. Instead of the function f of x, I have the function capital G of x. So the limit of this expression would be the derivative of the function capital G of x, in other words, g prime of x. And by the same token, if I asked you to find the limit as h goes to 0 of capital F of x plus h minus capital F of x over h, that would be the derivative of this function, capital F of x. In other words, capital F prime of x. So I just want to remind you of that. It will come up later on when we're doing our picture proof. Okay, let's go ahead and give at least an intuitive argument for why the fundamental theorem of calculus is true. Here's our picture proof, and notice proof is in quotes because it's not a rigorous proof, it is more of a persuasive argument of the fundamental theorem. Here's my little question at the top: how can this marvelous theorem, meaning the fundamental theorem of calculus, be true? And that's what we're going to try to argue here. And we're going to use pictures to support our argument. Well, what is it we're trying to prove? What does the fundamental theorem say? Remember, it says that if we have a nice continuous function on the interval from a to b that's above or on the x-axis on that interval, then this exact green area underneath the curve is equal to capital F of b minus capital F of a, where capital F of x is an antiderivative of little f of x. So that's what we want to show. All right, and we're going to do it in two parts, in two steps. Okay, let's go ahead and look at step 1 of our proof. And we're going to start by defining a function capital F of x, and it's defined in sort of a weird way that we don't usually define functions. Capital F of x is going to measure how much area is under the curve little f from 0 up to x. So it counts basically the output value of this function capital F is how much green area there is under the curve from 0 up to x. And I hope you can see that f really is, capital F is a function of x, because if I chose a new x, say an x that's a little bit to the right of this one, then I would be measuring the area from 0 up to that new x, and you notice I'd get a different area, so I would get a different output value f of x. As I move this x to the right, I'm getting different areas under the curve, and so I'm getting different output values for f of x. So capital F is a function of little x. It's just defined in a really different sort of way. Well, let's see if we can describe in terms of capital F of x what the area under this curve, it's still the curve little f, the area under this curve from 0 up to b. Well, we said capital F of any x is the area under f from 0 up to whatever x that is. So if I'm going from 0 to b, that means that the x value that I'm choosing is just b. And this green area would be capital F evaluated at b. That would just be the area under little f from 0 up to b value. Okay, well, what about this? Can you tell me how to write that in terms of capital F? Well, this is the area under little f from 0 up to a, and so it would be capital F evaluated at a. What about this area under the curve little f from a up to b? Is there a way to get that from these two pictures up here? In other words, I want the area between this vertical line at A and this vertical line at B. And I hope you can see that one way to get that is just to subtract these two areas. If I took this big area and subtracted off this chunk, so I subtract off this red chunk, you end up with the area that's between the vertical lines x equal a and x equal b. So this area would be the original area that I had here, f of b, minus the area that I have over here. So I could write this is equal to capital F of b, this whole area, minus capital F of a, this little area here, and that gives us the area in between those two. And that's really all there is for step 1. If we define f of x this way as the area under our curve from 0 to x, then this area from a to b is going to be capital F of b minus capital F of a. So that's what this green area is equal to. But what haven't we shown? We haven't shown that capital F is an antiderivative of little f. So kind of the crux of the proof comes into showing that, and that's what we're going to try to show in the next step. So let's go to the next page and see if we can do that last thing. That's what I'm calling step 2. We still need to show that this capital F of x that measures the area under f from 0 up to x, we have to show that that is an antiderivative of little f of x. Okay, well, how are we going to do that? Well, we're going to do it again using pictures. So first of all, remember that capital F of x, what is that? That's the area under the curve from 0 up to x. So this green shaded area here is capital F of x. What if I increase my x by a small amount? So here's the x value that I originally had, and I'm going to move to the right a small number of units h. First of all, what would this value right here be? If I'm at x and I'm going h units to the right, then this x coordinate would be x plus h. Okay. And now notice that I'm doing the area underneath my curve y equal f of x from 0 all the way up to x plus h. So this new green area would be capital F evaluated at whatever my ending value is, which is x plus h. Okay, based on those two pictures, doing something similar to what we did on the last page, can you tell me how to write this green area? It's sort of this little piece of area that's in between this area and this area. Can we write that in terms of capital F? And yeah, if I took this whole area from 0 all the way up to x plus h, and I subtracted off this area from just 0 up to x, I would end up with the area in between, this sort of strip of area from x to x plus h. So I'm going to take this area, capital F of x plus h, and I'm going to subtract off this area, capital F of x, and that should be the area of the strip that's between the line x and x plus h. Okay, keep that in mind. Okay, let's go to the next page, and you'll notice this picture in the upper left is exactly what we had at the bottom of the last page. It was the area of this green strip, this area under the curve little f from x to x plus h, and we said that area is capital F of x plus h minus capital F of x. So that expression is the area of this green strip. Now what I'm going to do is look at the area of something else over here, the area of a rectangle that is underneath my curve little f. And I can see that this rectangle does not have the same area as this strip, but it's approximately the same area. It's not a great approximation, but it's an approximation. So the area of my strip is approximately the same as the area of this green rectangle. Well, what is the area of this rectangle? Well, the area of any rectangle is its height times its width. And I can see what the width of this rectangle is. It's h. I've made it exactly the same as the width of my strip. So the width of this rectangle I can fill in as h. And then to find the area, all I need to do is figure out how high this rectangle is. And it looks as if it's the height under my curve right here at the value x. And since this is the curve y equal f of x, that means that the height of this rectangle is just f evaluated at that x value, namely f of x. So the height of this rectangle is f evaluated at whatever x value I'm at here. So let me go ahead and write that down, that the area of this rectangle is little f of x times h. So that's the area of my rectangle. This is the area of my strip. We said those two are approximately equal to each other. So capital F of x plus h minus capital F of x is approximately the same as little f of x times h. Well, if the left side of this line is approximately the same as the right side, then if I were to divide the left side by h, that should be approximately the same as if I divide the right side by h. So the left side is approximately equal to the right side. Left side divided by h should be approximately equal to the right side divided by h. And you notice on the right side that I have an h over h. I could cancel those. And what do I end up with? I end up with the following, that capital F of x plus h minus capital F of x divided by h is approximately equal to, and all I have left on the right side is little f of x. Well, we said they're approximately equal, but it's not a very good approximation. And how would I get a better approximation? That leads me to this question. As h gets smaller, what happens to our approximation? So I've drawn exactly the same picture that I had up here, but with a smaller h value. So I have a skinny strip here and a skinny rectangle here. You notice that we said these two things weren't exactly equal to each other. How far off are they? Well, they're off by quite a lot. Here's the error right here. This is the amount that my rectangle is too small. So this is the error. And it looks like a fairly large error. But what happens when I make h smaller? Notice that it's only off now by this amount, and we get a smaller error. So that looks better to me. Now this side of this expression should be closer to this side because this area is closer to this area. So as h gets smaller, the answer to our question, we could say as h gets smaller, this approximation that we set up gets better. The area of my approximating rectangle gets closer to the area of my actual strip, and when we divide through by h, this side here gets closer to this side. So this approximation gets better. Well, if I were to draw another picture with h even smaller, I think you can imagine what that would look like. This triangular shaped error is going to be even smaller if I make my h smaller on both of these two pictures. And so this approximation would get even better. In other words, the left side would get even closer to the right side. So let's go ahead and go to the next page and see what we're going to do next. The question is, in the limit, if I were allowed to allow h to go all the way to 0, what would happen to my approximation? Let me look back at this picture just one more time. Think of this picture where h shrinks all the way to 0, and this becomes an infinitesimally skinny little strip. And think of h shrinking all the way to 0 here. This red error that I had up the top would shrink down to an error of 0. And so the rectangle over here would have exactly the same area as the strip. And what does that mean? When we divide both sides of our areas by h, it means that this side would end up being exactly the same as this side. It would no longer be an approximation. It would actually be an equals. So the expression on the left would become equal to the expression on the right as h shrinks all the way to 0. So let's go ahead and go. At the top of the next page, I ask the following question. In the limit, if we were to let h go all the way to 0, what would happen to our approximation? If we look at the picture at the bottom of the last page just for a moment, we can probably answer that question. So imagine these pictures that I have down here at the bottom where I've let h shrink all the way to 0. When I do that, this strip becomes infinitesimally skinny, the width shrinks all the way to 0, and this rectangle becomes infinitesimally skinny, its width also shrinks all the way to 0. And in particular, I want you to notice what happens to this red error that we have here. As h shrinks to 0, this little red area gets smaller and smaller, and eventually, as h goes all the way to 0, the error will go all the way to 0. In other words, this approximating rectangle will become equal in area to the area of this strip. What does that mean about our approximation that we wrote up here? Well, we said as h gets smaller, this approximation gets better. And when h shrinks all the way to 0, this is no longer an approximation. The left side is not approximately equal to the right side. It becomes an equality. The left side will be equal to the right side. Well, let's write that down on the next page. So we said on the last page, this was our expression that was on the left-hand side, capital F of x plus h minus capital F of x over h. We said that was approximately equal to little f of x. But if we found the limit of this expression as h shrinks all the way to 0, we said that the error will shrink to 0 And this approximation will no longer be an approximation, it will actually become an equals. So the limit of this expression as h goes all the way to 0 would be equal to little f of x. Okay. But what is this expression, the limit as h goes to 0 of capital F of x plus h minus capital F of x divided by h? Well, that's something that we reviewed just before we jumped into this picture proof. This thing on the left-hand side is exactly our original limit definition of the derivative. And it'll be the derivative of whatever function I have involved here, in this case the function capital F of x. So the limit as h goes to 0 of capital F of x plus h minus capital F of x all divided by h, by definition, is the derivative of capital F of x. In other words, it's f prime of x. And that is equal to little f of x. Okay, well, what does that tell me? I'm saying that the derivative of capital F of x is little f of x. And what does that mean about capital F of x's relationship to little f of x? It's the function whose derivative is little f of x. In other words, capital F of x is, and I have two blanks here, and what should go in this blank? It's an antiderivative of little f of x. It's the function whose derivative is equal to little f of x. And that was the second step of our proof. That's what we wanted to show, was that capital F of x was an antiderivative of little f. And let's just go back and review what we were trying to show, just to summarize the two steps that we have done here. If you remember, when we started this picture proof, I said what we wanted to show was that the area was capital F of B minus capital F of A. That's what we did in step 1, where capital F of x is an antiderivative of little f of x. And that's what we just showed in our step 2, that capital F was an antiderivative of little f. So those are the two things that we needed to show, and we can say QED, we are done with this picture proof. So that concludes our proof of the fundamental theorem of calculus. I do want to remind you that what we did was really more of an intuitive argument. It was a picture, we called it a proof, but a proof in quotes. And it is, of course, possible to prove this theorem rigorously, and I've included that proof at the end of this handout. So if you have the handout that goes along with the video, please look at the end and take a look at that rigorous proof for the fundamental theorem. Okay, let's go ahead now and look at a specific example. Well, we've done some examples already, but I'd like us to do one that's maybe a little bit more complicated. We're going to find the exact area of this shaded region. Now we get to use the fundamental theorem of calculus, and we've proved that theorem. Okay, if I want the area that's shaded here, it's under this curve, 6x squared minus 12x plus 7. I do want to check that the conditions of the fundamental theorem are met. And f of x, you notice, is a polynomial, so it's continuous everywhere. So in particular, it's continuous on this interval from -1 to 2. And I can see that it's also always above the x-axis on that interval from -1 to 2. Cool. So that means I can use the fundamental theorem of calculus to find that area. And why don't you go ahead and pause the video and see if you can find that area using the fundamental theorem, and then we'll go through it together. Well, let's go ahead and try this one together. I know that it's going to be the definite integral from -1 to +2 of this function, 6x squared minus 12x plus 7. It's the same process we've done before, but it is a more complicated function with a bunch of terms in it, and that's why I wanted you to give it a try. Let's see, I'm going to be finding antiderivatives, so I have a factor of 6 that gets carried along, and I'm finding the antiderivative of x squared using the power rule. That'd be x to the third, and I need a 1/3 out in front. Minus 12 times, that's a constant multiple, so it gets carried along. This is really x to the first power, so I increase that by 1. It'll be x squared, and I need the reciprocal of that new power out in front, so I need a factor of 1/2 out in front. And 7, the thing I have to differentiate in order to get 7 is 7x, so the antiderivative of 7 is 7x. And then remember that we want to go ahead and put our vertical line, which simply means we're done finding the antiderivative, but we want to remember that we still have to plug in. We are doing a definite integral rather than an indefinite integral. Well, let me just simplify this a little bit before I plug in. Let's see, this would be 2x cubed minus 6x squared plus 7x. And I want to take that whole expression and evaluate it first at my upper limit of 2 and then at my lower limit of -1. So first I plug a 2 in. So let me go ahead and plug 2 in for all of the x's. Let's see, 2 times 2 cubed would be 16, minus 6 times 2 squared would be 24, plus 7 times 2 would be 14. So that's evaluating this at the upper limit. I subtract the value at the lower limit, means I plug in -1. 2 times -1 cubed would be a -2. I guess I'd get a -6 and a -7. And then we just go ahead and compute that, and when we add it all up, I got a value of 21. I added it up correctly. And so this green shaded area is exactly equal to 21 square units. If we're working in feet, it would be 21 square feet. Okay, let's go ahead and look at the next page. And I think we have a couple other examples to do that are slightly more challenging examples. At the top here, I am asked to find the integral from 0 to pi over 4 of secant squared x, and also interpret that as an area. So let's try to do that. Well, I can certainly do this definite integral. Secant squared x is definitely going to be something that's not negative because it's whatever the value of secant x is squared. So I definitely have something that's not negative on this interval. And you might remember that secant x is 1 over cosine x. I'm just going to jot that down here. Secant x is 1 over cosine x. So the only place secant squared x would be undefined is somewhere where cosine of x is equal to 0. That would give me a 0 in the denominator. And I believe on this interval from 0 to pi over 4, we're okay. Cosine of x is defined everywhere there. So that's just sort of a long way around saying that secant squared x will be continuous on the interval from 0 to pi over 4. In this picture down here, I'd be going from 0 to pi over 4 radians, which is 45 degrees, and secant squared x will be a continuous function that's above the x-axis everywhere on that interval. So I can go ahead and find the antiderivative here, and I have to think backwards. I have to think, what do I have to differentiate to get secant squared x as an answer? And I would have to differentiate tangent x. And I've now done my antiderivative, so I'm going to draw my vertical line. I'm done integrating, and just put my limits there so I don't forget to plug in those limiting values. Okay, great. So that would be tangent evaluated at the upper limit, pi over 4, minus tangent evaluated at the lower limit of 0. Tangent of pi over 4 is tangent of 45 degrees, which, if you know your special angles, is equal to 1. Tangent of 0, I always think sine 0 over cosine 0. Sine of 0 is 0, divided by cosine of 0 is 1. 0 over 1 is 0. And so I get a value of 1. So the value of this definite integral is the number 1. But now we're asked to also interpret that as an area. Well, it has to be the area underneath this curve, f of x equals secant squared x, on the interval from 0 up to pi over 4. So it's just a matter really of saying it's the area under this curve from 0 to pi over 4, and we could even graph what that area looks like. Secant x, as I mentioned, is 1 over cosine x. Secant squared x is going to be 1 over cosine squared x. And if you go ahead and graph that, it will have problems at pi over 2 and minus pi over 2. Those are places where cosine is equal to 0, and so secant squared x would actually be undefined. And if you remember kind of back to your trig class, those are places where the secant function has vertical asymptotes. Now, if we graph secant squared x rather than secant x, we'll get something that is always positive, and the graph ends up looking roughly like the following. I just plugged in a few points. I plugged in 0, pi over 4, and I think I plugged in pi over 3 because that's an easy place to evaluate secant squared. So I just plugged in some values. When I plugged 0 in, I got 1 for the secant squared x value. When I plugged in pi over 4, I got 2, and when I plugged in minus pi over 4, I also got 2 as an output. And when I plugged in, I think I also plugged in pi over 3, which is 60 degrees. And when you plug in pi over 3, you get 4 as an output. And if you plug in negative pi over 3, you also get 4 as an output. There's a symmetry across the y-axis to this graph. So the graph looks something like this. And I won't worry too much about the details of graphing that perfectly. But what we have just found with this definite integral, this answer of 1, was really a certain area. It was the area underneath this curve, secant squared x, from 0 up to pi over 4. And let's see, when I plugged in pi over 4, I got 2 as an output value. So it was this green shaded area. It's not a very perfect graph. And so now we've found the value of this and said that that's really could be interpreted as the area under the secant squared graph from 0 to pi over 4. This green shaded area turns out to be exactly equal to 1. Okay, I want you to go ahead and think about this second example. You're not asked to interpret it as an area, just to find that definite integral, and it's a slightly more challenging one, so pause the video and give that one a try. Okay, let's go ahead and try this one together. One thing I will mention is that if you were to graph this on a y versus u axis, where y is this function that's inside the integral, u cubed plus 1 over u, we would be looking at the interval from u equals 1 up to this upper limit, u equals 2. So whatever this graph looks like, we're looking at it on that interval, and I can see that for those values of u from 1 to 2, this expression u cubed plus 1 over u will always be positive. So whatever the graph looks like, I'm not going to bother to graph it carefully. It's definitely above the u-axis on that interval, and it will also be continuous everywhere on that interval. The only place this expression would fail to be continuous is where the denominator is 0, and that would be when u equals 0, and that's not in this interval from 1 to 2 that we're considering, that we're integrating over. So we can interpret this as the area under this curve, u cubed plus 1 over u, from u equals 1 up to u equals 2 if you found this shaded area here. Well, we weren't asked to interpret it as an area, so let's just go ahead and find the value of this definite integral. And the first thing I'm supposed to do is find an antiderivative. But unfortunately, we have no way to integrate a quotient. There is no quotient rule for integrals. We learned that back in section 4.9. So I have to rewrite this expression first before I try to find an antiderivative. I have to get it into a form where I have a rule that allows me to find the antiderivative. And one way to do that would be to break this up into two fractions, u cubed over u plus 1 over u. I'll put parentheses around that and put du. Okay, let me go ahead and simplify that a little bit. It would be the integral from 1 to 2 u cubed over u is just u squared. This I could write as u to the negative 1, but remember the power rule works for every power except for negative 1. So I'm going to actually leave this as 1 over u. If you tried to use the power rule, if you tried to rewrite it as u to the negative 1 and use the power rule, hopefully you notice that the power rule gives you something that's undefined as the multiplying factor out in front. And if you got stumped, that's because that's the one value of our exponent that the power rule does not work for. The power rule will work on u squared. The integral of that would be 1/3 u cubed, so that would be an antiderivative of u squared. And then remember the antiderivative of 1 over u would be ln of absolute value of u. So for that one power, u to the negative 1, it's really the function 1 over u, and an antiderivative of that would be natural log of absolute value of u. We get to take any antiderivative that we want to. I am choosing the antiderivative with the integration constant c of 0. So there are my antiderivatives of each term. And I've done my integrating, so I put my vertical line and then just stick my limits on there so I don't forget to plug in those limits. Okay, well let's go ahead and plug in. We plug in the upper limit first in place of all the u's that I see. So I would get 1/3 times 2 cubed, that would be 8/3, plus the natural log of absolute value of 2. Well, absolute value of 2 is 2, since 2 is positive, so that would just be the natural log of 2. So that's what I get when I plug in the upper limit. When I plug in the lower limit, let's see, I'll have 1/3 times 1 cubed, so that would just be 1/3, plus ln of absolute value of 1, which is ln of 1. Okay, so what does that give me? Let's see, I'm going to have 8/3, and I'm going to have a minus 1/3, so I'm going to end up with a total of 7/3 here. And then I have ln of 2, so I'm just distributing this minus sign in my head. And I have a minus ln of 1, but ln of 1, you may remember, is just equal to 0. So I would end up with an answer of 8/3 minus 1/3 is 7/3 plus ln of 2. And that would be the exact value, if I can try to fix that up a little bit so that we can see it, that would be the exact value of this definite integral. 7/3 plus ln of 2, and you could throw that into a calculator to get an approximate value. Okay, let's go ahead and go to the next page. So on the next page, I have 2 more problems, again rather challenging ones. In this one, I'm asked to find the value of this definite integral and interpret it as an area. And in this one, I'm given the area and asked to find what that area is using a definite integral. So I'd like you to pause the video and give both of those a try, and then restart the video if you get stuck, and we'll go through it together. Well, let's go ahead and look at this top one. I'm asked to find the definite integral from 0 to ln of 5, and remember that's just some number, of e to the x dx, and then I'll worry later about interpreting that as an area. Well, okay, if I'm asked to find this definite integral, that means that I want to find an antiderivative of e to the x. Remember, e to the x is its own antiderivative. So the antiderivative I'm going to choose of e to the x is e to the x, where again I'm choosing my integration constant c as just a 0. Well, I've done my integrating, even though I get the same function. It's just because e to the x is its own antiderivative. But I have to put my vertical line and my limits to remind myself that I still need to plug those upper and lower limits in. Remember that we always plug in the upper limit first, so I would have e to the ln of 5 minus e to the 0. So e to the x evaluated at ln of 5 minus e to the x evaluated at 0. Okay, now I want you to realize that this first expression simplifies. Remember that the natural log function and the natural exponential function are inverses of each other. So if I start with 5, do ln of 5, and then plug that into the e to the x function, what happens? The ln and the e undo each other, and I actually just get the number 5 here. And what about e to the 0? Well, anything raised to the 0 is equal to 1, so I get 5 minus 1, or 4. So that's the value of this definite integral, and it's the area of something. What's it the area of? That's the other part of the problem, is to interpret this as an area. And remember that to interpret this as an area, you want to say, okay, it's going to be the area under whatever function I am integrating. So it's going to be the area under the y equals e to the x curve from 0 to ln of 5. Okay, so from 0, ln of 5, by the way, I think I plugged that into a calculator, is about 1.6. So if this is 1 and this is 2, ln of 5 would be right about here. Ln of 5 is approximately equal to 1.609 something. So we are finding the area under this curve, y equal e to the x, from x equals 0 up to x. So we would be finding the area under the y equal e to the x curve from x equals 0 up to x equal ln of 5, or approximately 1.6. Well, what does this graph look like? We've graphed that many times. When I plug 0 in, I get 1 as an output. When I plug in 1, I get e, so that's about 2.7. And so I'm going to get a graph that looks roughly like this. That's my graph of e to the x, at least roughly. And this number 4 would be the area under that curve from x equals 0 to x equals roughly 1.6. So it would be this shaded area from x equals 0 up to x equal ln of 5. Okay, let's go ahead and look at the second example, and if you haven't had a chance to try that yet, pause the video and give it a try. And again, it is a more challenging example. Okay, let's go ahead and try this together. Here we're asked to find this shaded area underneath the curve 1 over x squared plus 1. Well, I notice that this curve is definitely above the x-axis on this interval from -1 up to root 3 that's shaded in. And I also notice that it is a continuous function. It's a rational function, and the only place a rational function would be discontinuous is where the denominator is 0, but x squared plus 1 is always positive. So the denominator is never 0 for any value of x. So great, that means I can use the fundamental theorem of calculus to find this area, as long as I can find an antiderivative. So the area should be the definite integral from -1, my starting point, to root 3, that's where my area ends, of this function, 1 over x squared plus 1 dx. Okay, that looks good. Now I have to think backwards and find out whether I know how to find an antiderivative of 1 over x squared plus 1. But remember, this was actually one of our special formulas from our section 4.9 on antiderivatives. What is this the derivative of? It's the derivative of one of our inverse trig functions. It's the derivative of the inverse tangent of x. So now I found an antiderivative. I want to evaluate that from x equal -1 to root 3. And remember that we always want to plug in the top limit first, so I put in the upper limit. That would be the inverse tangent of square root of 3, and I subtract the value of my antiderivative, inverse tangent, evaluated at the lower limit, -1. Well, of course, now I have to remember a little bit of trigonometry, some stuff from back in pre-calculus. I have to remember how to find the inverse tangent of root 3 and how to find the inverse tangent of -1. Well, you might remember that if we set theta equal to the inverse tangent of some number x, what does that really mean? That really means that tangent of theta will be equal to x. If you want to, you can think of taking tangent of both sides of this equation. You get tangent theta on the left side. You get tangent of the inverse tangent of x on the right side. The tangent of the inverse tangent, those are inverse functions, they undo each other, and we just get x on the right-hand side. So when I say theta equals the inverse tangent of x, it means I'm looking for an angle theta whose tangent ends up being that number x, the number that's inside my inverse tangent function. Remember also, though, that all of our inverse trig functions had restrictions on their domains and their ranges. So I'm looking for an angle theta whose tangent is x, but I must choose an angle theta that is in a certain range. So remember that theta has to be somewhere between pi over 2 and negative pi over 2 for the inverse tangent function. So I'm looking for an angle theta whose tangent is x, where theta is some angle between minus pi over 2 and positive pi over 2. And that was part of our definition of what we mean by the inverse tangent of a number. Okay, well, let's go ahead and see if we can do at least this first one here. I want the angle whose tangent is root 3. So I'm looking for an angle theta such that the tangent of theta ends up being root 3. Okay, well, of course, you have to know your sine, cosine, and tangent of the special angles to recognize that the angle whose tangent is root 3 is 60 degrees. So tangent of 60 degrees is equal to root 3. Actually, in my head, I remember sine of 60 is root 3 over 2, cosine of 60 degrees is 1/2, and so sine over cosine, which would be the same as tangent of 60 degrees, is root 3 over 2 divided by 1 over 2, which would reduce to root 3. Well, that's a long way to do it, but it's just the way I do it in my own head. So the angle here, theta, that we want, the angle theta whose tangent is root 3, would be the angle 60 degrees. We want it as a pure number, so we want to write that as radians. So this angle theta here would have to be equal to pi over 3 radians. Now let's go to the inverse tangent of -1. I'm looking for an angle theta whose tangent is equal to -1. Well, that's a little bit trickier. I can see that if I'm looking for an angle somewhere between pi over 2 and minus pi over 2, I'm looking in the first and the fourth quadrants. And tangent is negative in the fourth quadrant. So I'm really going to be looking for an angle theta that's in the fourth quadrant. I usually look for the reference angle first, and I remember that tangent of 45 degrees is equal to a positive 1. I want the same angle but down in the fourth quadrant. So I would want an angle that's down 45 degrees from the positive x-axis. What angle is that? That would be the angle minus pi over 4, minus 45 degrees. So the correct reference angle is 45 degrees, but if I want this to come out to be negative, I better pick an angle in the fourth quadrant. Tangent of minus 45 degrees would be equal to -1, and that's the angle that I want. So this angle here, whose tangent is -1, would be equal to minus 45 degrees, but I want that as a pure number in radians, so that would be minus pi over 4. So that's a little bit of work on the side. You might be pretty good at doing these inverse tangent calculations, and then this won't present any problem, but I wanted to go through it carefully in case you've forgotten some of those details about inverse trig functions. Okay, so we plugged in and we found out what these values are. This first term turned out to be pi over 3, and then I'm subtracting this second term, which turned out to be minus pi over 4. Now I just go ahead and simplify. That would be pi over 3 plus pi over 4. And if I get a common denominator of 12, let's see, that'd be 4 pi over 12 plus 3 pi over 12 would be 7 pi over 12. And that would be this exact area. So the area, green area right here, turns out to be 7 pi over 12. And you could certainly plug that into a calculator to get an approximate value. Okay, let's go ahead and look at the next page. Okay, well, let's go ahead and look at the next page. And on the next page, I have kind of a different sort of example. It's an example where the work has been done, but there's something that's wrong. So I want you to try to think about the following. It says, what's wrong with this calculation? Maybe a friend of yours in another calculus class was asked to do this definite integral, the integral from -2 to 2 of 1 over x squared dx, and he went through the whole problem and ended up getting a negative answer. And he thought that was sort of curious because he could see that the function 1 over x squared is always positive. So he said to you, how come the function's always positive? Then I'd be finding the area from -2 to 2 underneath the graph of this function. Why is it coming out to a negative answer? So I want you to pause the video and think about what could be wrong in his calculations or in his thinking or in his assumptions. Well, let's go ahead and think about this together. If you just look at his calculations, what the student did was he saw that he had a definite integral to do, and he dove in and he did it. So he said 1 over x squared. Well, I'm going to write that as a power of x so that I can use the power rule to find the antiderivative. That's a great idea. So he said, okay, x to the -2. He used the power rule correctly. He added 1 to the exponent, -2 plus 1 would be -1, and did 1 over the new exponent out in front. That looks perfect. And he simplified this to make it easier to plug in his limits. So he said -1 over x from -2 to 2 is the antiderivative that he's trying to evaluate. So now down here, this also looks okay to me. He said, okay, I'm evaluating the function -1 over x first at the upper limit of 2, so he plugged in the 2, perfect. Then I subtract the value of this function evaluated at the lower limit, so that would be -1 over, and he plugged in the lower limit, -2. That looks good. So he has -1/2, 3 negatives stacked up here give us another -1/2, and he got -1. Well, all of the mechanics here are correct. But there is something wrong with his analysis of the function he was originally given to find the definite integral of. It's true that this is always positive everywhere that it's defined on the interval from -2 to 2. So we're thinking about this function from -2 to 2, but can you see something that he didn't check about this function? So let's see if we can figure out what's wrong with what the student did. Well, if you're really stuck, one way of thinking about it would be to think, well, the student was thinking, gee, shouldn't I be getting the area underneath this curve, f of x equals 1 over x squared, or we could think of it as y equals 1 over x squared. Well, let's go ahead and try to graph this function, and I think we'll see pretty quickly what the problem is. If I try to graph this, let's see. Well, if I plug in something like x equal 1, I would get an output of 1. And if I plug in -1, I also get an output of 1. So those are a couple points on my graph. If I were to plug in 2, I get 1 over 2 squared. That's a fourth. And so I'm kind of close to the x-axis here. And when I plug in -2, I get the same thing. So I just go up a fourth of a unit. And if you want to, you could even plug in the value x equal 1/2. And you notice you'll get 1 over 1/2 squared. That's 1 over 1/4. Invert and multiply, and I get an output value of 4. And the same thing would be true at x equal -1/2. You get an output value of 4. Well, let me go ahead and start to connect these points together, and you start to see what kind of function we've got here. and it looks like something weird is happening at x equals 0. In fact, it looks as if that may be a vertical asymptote. So let's go back and think about the function a little more carefully than the student did before he dove in and just started trying to find antiderivatives and plugging in his a and his b value. This function is a rational function. And where is a rational function discontinuous? It's discontinuous wherever the denominator is equal to 0. So notice that there's a problem because f of x equals 1 over x squared, its rational function, is not continuous on this interval from -2 to 2. And that's where the real problem lies in thinking that he can just go through here and mechanically integrate this thing. I'll say in particular, it's not continuous at x equals 0, and we can see from the graph that at x equals 0 it appears that there is a vertical asymptote for this curve. So unfortunately, we can't just integrate 1 over x squared dx from -2 to 2 because that interval of x values includes a place where the function fails to be continuous. This type of integral where you have a discontinuity and your function essentially goes to infinity, the output values go to infinity as we get close to 0, is what's called an improper integral. And so it is actually possible to do this problem, but you won't learn how to do that until next semester. You have to break it up as an integral from -2 to 0 and then another integral from 0 to 2 and use a limiting process that we haven't talked about. So it is actually possible to compute the value of this integral, but it requires techniques that you won't learn until second semester calculus. And if you think about the area underneath this curve, it's sort of weird, isn't it? We're looking at the area under this curve from -2 to +2, and it looks to me as if it's what's called an unbounded region. And what do we mean by an unbounded region? Well, as opposed to some of the problems that we looked at before, if we look at just the last page that we had here, you notice the regions that we were finding the area of were bounded. They had a boundary around them. They weren't just sort of open. The same thing here. This is a bounded region that we were finding the area of. So we know that these have a finite area. But the area that you're finding for this curve, because of this vertical asymptote and the fact that it's not continuous at x equals 0, actually looks like it is, you're trying to find the area of an unbounded region. There's no top to this. It would just keep going forever. And the same thing on the right hand side. If we went from 0 to 2, that area is also unbounded. It doesn't necessarily mean that we can't find the area of such a region. For this particular example, from -2 to 2 of 1 over x squared dx, it will turn out that using these techniques from next semester, you'll find out that the value of this definite integral is infinite. In other words, this unbounded area here is infinite in size. Not all unbounded regions have an infinite area, but this particular one does. And so this answer that the student got of -1 actually is a meaningless answer, and that's because the original function was not continuous on this interval from -2 to 2 that he was integrating over. The true answer to this question would actually be positive infinity. The area between this curve and the x-axis turns out to be infinite. So that's just to kind of warn you that you want to think a little bit before you just dive in, because you may get an answer that is meaningless if your function here is something that is not continuous on the interval that you're looking at. By the way, if he had been asked to do a different problem, say he had been asked to do the integral from, say, 1 to 2 of 1 over x squared dx. Would that have been okay if he had just dove in and started to find the antiderivative and plug in his a and b? That would be okay. 1 over x squared is only discontinuous at 0, and that is not included in the interval from 1 to 2. And in fact, you can see that that would be a nice bounded region, and you'd be finding the area under 1 over x squared from 1 to 2, the area of this little section right here. So it's just a good idea to think about your function. Make sure that if you're trying to find an area of a region, that you have a function that's always above the x-axis on the interval from -2 to 2, and that your function is actually continuous on that interval. Otherwise, the answer you get may have no meaning. Okay.